Hi, I'm Jay. Today I'm going to talk about application of eigenvalue and eigenfactors in linear algebra. So, if we have the a recursive equations like gk 加 n is gk plus n is a1 times gk plus n minus 1 and a2 times gk plus n minus 2 and so on. And this equation, we call it an nth order linear homogeneous difference equation with constant coefficients because its efficient is constant. So, and this equation have initial conditions. We know the g0, g1, g2, and 2, gn minus 1. So let uk is a factors, and these factors equal to gk plus n minus 1 and gk minus plus n minus 2 and 2 gk. Then uk plus 1 is gk plus n and gk plus n minus 1 and 2 gk plus 1. And the relationship between uk plus 1 and uk can be represented by a matrix multiplication. So it's actually uk plus 1 is actually a matrix A times uk, and this matrix A is like this one. The row of A is A1, A2 to AN because this is the definition of this definition is from this equation, and the so on is a identity matrix because the rest of the term is the same as the uk. Okay, so we have this matrix A. So the first step, if we want to calculate the Gn terms, we need to first diagonalize A. So how to diagonalize A? It's actually by calculate the eigenvalue and eigenfactors of A. So x1, x2 to xn is the eigenfactors of A, and the lambda 1, lambda 2 to lambda n is the eigenvalue of of A, and this is the inverse of S. Then we write u0 by u0 as these terms, and is c1 x1 plus c2 x2 and so on to cn xn is actually equals to sc, where c is equal to s inverse of s times u0. And uk is actually ak times u0, and ak is like this. So we can move the terms like this, and we can get this equation. And uk, or we can write it by this way. uk is ak times u0, and ak is actually like A is as I said before, A is equal to S times lambda times S inverse of S. And if we have multiplied this by k times, we get S lambda S inverse of S, S lambda inverse of S, so and so on. S lambda inverse of S, and this will become I, this will become I, this will become I. So final result of AK is actually S of S times the power of lambda to the K and inverse of S. So this is the final result. And lambda is a diagonal matrix. So lambda, the power of lambda to the K power is lambda 1 K power, lambda 2 K power, and so on to lambda n K power. So this is very easy to solve. So by diagonalize the matrix A, we can easily get the AK. Okay. And this is shown by this. Okay. And yeah. So let's have a short example. If we have the equation like this, gk plus 3 is equal to -2 times gk plus 2 plus gk times 1, gk plus 1 times 2 times of gk, and g0 is 6, G1 is negative 5, and G2 is 15. So let's let UK equal to GK plus 2, GK plus 1, and GK. This is the factor UK. And UK plus 1 is like this one. And the relationship between UK plus 1 and UK can be represented by a matrix. Can be represented by a matrix A, like this one. So the first row is the coefficients of this equation. So it's negative 2, 1, and 2. And the rest of the row is basically an identity matrix. So 1, 0, 0, 1, 0, 1, 0. So this is A. And we need to diagonalize this matrix A. So we need to first calculate the eigenvalue of this matrix. So we can solve eigenvalue by solving this equation determinant of A minus lambda times I equals to 0. So the solution to this equation is when lambda is negative 2, negative 1, or 1, then this equation will be 0. And this 3 number is the eigenvalue of this matrix A. And we get its eigenvalue, so let's get from his eigenvalue, we can get the eigenfactors of this matrix. So the first eigenfactor is 1, 1, 1. And the second eigenfactor is 4, minus 2, negative 2, and 1. And the final eigenfactors is 1, minus negative 1, and 1. And yeah, so we get these 3 eigenfactors and eigenvalue. So U0 can be represented by C1x1 times C2x2 times C3x3, and C1 is like this, C2 is like this, C3 is like this, and it needs to equal to the initial condition, like this 3 numbers. So it's 15, negative 5, and 6, and it equals U. By solving this equation, we get C1, C2, C3. C1, C2, C3 is 2, 3, and 1. And the third step is we have this, we make the power of A to the k powers and times U0. And this is U0. And U0 is equal to C1x1 times C2x2 times C3x3. And we move this part to this part. So AK times x1 is actually lambda 1 to the k powers to x1 times C1, and the rest of the terms like this. So lambda 1 k to the k power of x1 is actually 2 times x1, and